Physicists believe that when time began, at the moment of the Big Bang, matter and antimatter were created in equal amounts. And based on recent measurements made at CERN Laboratory in Switzerland, it seems there is perfect symmetry between the two, which they say implies that our universe should not exist. What? Okay, here to talk about this perhaps disconcerting discovery is CBS News science and futurist contributor and theoretical physicist Michio Kaku. All right, Professor Kaku, so can you explain, first of all, what antimatter is and how is it different from the matter that we interact with every day?
Well, there's a Nobel Prize out there if you can figure out how this thing works. Antimatter is the mirror image of ordinary matter. It's extremely rare. If I had some in my hand, it looked like ordinary matter, has the same chemical properties, except if I touch it, it would explode and destroy all of New York City, parts of Connecticut and New Jersey. Every Star Trek fan knows that this is the greatest energy source in the universe, matter-antimatter collision.
Okay, all right, so that's it. Well, what is it about this symmetry between matter and antimatter that, leads CERN's physicists to this conclusion that we shouldn't exist, the universe shouldn't exist?
Well, at the instant of the Big Bang, there should have been equal quantities of matter and antimatter, which annihilated, driving the Big Bang. So, by rights, we shouldn't be here.
Right.
Because we have more matter than antimatter in our sector of the galaxy. We've looked for anti-galaxies. We've looked for anti-planets. We don't see any.
I don't even understand what that means, but okay, go ahead. Antimatter, anti-planets, because they would be made up of anti.
That's right. In fact, we see no evidence of that at all. So physicists say by rights we shouldn't exist. This means that at the instant of the Big Bang, there was a slight overabundance of matter over antimatter, and here we are as a consequence. Now, why? This is one of the greatest mysteries in all of physics. We are clueless to understand why. And like I said, if you want to win a Nobel Prize, figure this one out. Why was there's a slight overabundance of matter over antimatter?
Yeah, all right. Well, tell us more about these experiments that CERN is doing to answer, or at least try to answer, these questions.
Well, they take an atom smasher and they take the energy out of it and put it into a bottle. It's called a magnetic bottle. You can actually trap anti-hydrogen, anti-electrons going around anti-protons. And when they measure the property of anti-hydrogen, it's exactly like ordinary hydrogen, except, of course, they would annihilate it if they touched each other. And that's so frustrating. You want to tear your hair up. They were looking for an asymmetry between matter and antimatter. They find none. And so that's the mystery. Why do we exist at all? By rights, we shouldn't be here. By rights, we should have been disintegrated at the instant of the Big Bang.
Yeah, well, I'm sure there are all kinds of theories out there, but what are physicists kind of focusing in on? Is there one theory, two theories that are kind of the main focus?
Well, the leading theory is something called string theory, which is what I do for a living. I'm one of the founders of the subject, in fact, years ago. But even string theory has a hard time because you have to sort of like put it in by hand. And we want the theory to naturally come out with this overabundance of matter over antimatter, which explains why we don't see anti-galaxies out there and anti-planets. But we have a hard time doing it. So right now, nobody has a convincing answer to this question, why should we be here?
Conscious, sentient beings.
It is, of course, a mystery as to why the universe exists in such an intelligible manner, but it suggests to me, at least, that there's a deep link between the universe, the grand scheme that's unfolding, and beings like ourselves. Somehow the universe has become self-aware. It's engineered the emergence of comprehending, thinking beings like ourselves who can come to know the universe.
Some people marvel at the fact that the universe has, over billions of years, given birth to beings who can appreciate its complexity. We can even ponder where and how we fit in.
We're all struck by the beauty and majesty of the natural world about us, the trees and the sky and the beauty of a sunset. It is awesome in its majesty. How can we make sense of it all? We need to look at the hidden subtext of nature, the mathematical relationships that underpin it, forming a sort of shadow world. Some people think of this as like a cosmic code.
Regardless of whether or not they believe in God, most scientists agree the cosmic code appears to exist.
everything in the universe is determined by the fundamental forces of nature. The strengths of those forces are characterized by numbers called fundamental constants that are so sensitive that if they changed by just a little bit, the universe as we know it wouldn't be here. For example, if the rate of expansion of the universe right after the Big Bang had changed by 1 part in a quintillion is 1 with 18 zeros after it, the universe would continue to expand or collapse back on itself, and none of this would be possible. To illustrate just how small a number 1 part in a quintillion is, imagine all the grains of sand on this beach. In fact, imagine all the grains of sand in all the world's beaches. That number's probably somewhere around a quintillion. In this analogy, if all that sand represented the rate of expansion of the universe right after the Big Bang, how many grains of sand would I need to add or subtract to wreck the universe? Just 1 grain, 1 in a quintillion. That's how precise things had to be for us to be here.
But even though the Big Bang was perfectly calibrated, intelligent life would never have formed if matter had spread evenly across the universe.
Had it been perfectly smooth, then there wouldn't be any clumps which would gravitate and form stars and galaxies. So we needed slight irregularities in the distribution of matter in the universe. Had those irregularities been much smaller, stars and galaxies wouldn't have formed. Had they been much larger, everything would have collapsed to form black holes.
But even with the right distribution of matter throughout the universe, life would still never have formed without a complex series of processes inside stars that converted helium and hydrogen into heavier elements like carbon that form the basis of all living beings.
Some of those stars explode, providing raw material with which to form new stars, planets, and ultimately life. Had the laws of physics been a little bit different, or even if the physical constants had been a little bit different from what they really are, this process of nuclear fusion and the explosion of stars might not have been possible, and we wouldn't be here discussing it.
I don't know a single scientist who would disagree with the statement that the world is exceedingly ingenious. Not just mathematical, not just beautiful, not just elegant, but the manifestation of something truly extraordinary.
Is the emergence of intelligent life an accident? The laws of physics, the nature of the physical environment, and the physical constraints of replication and mutation ensure that in a universe with the basic physical constants and laws of this one, carbon-based life forms with opposable digits, eyes in their heads, and large brains are bound to come into existence. But Conway Morris argues that the landscape of biological form, be it at the level of proteins, organisms, or social systems, may in principle be almost infinitely rich, but in reality the number of roads through it may be much, much more restricted. There are only some feasible roads through protein hyperspace because of physical constraints that force a convergence of paths upon mutating organisms. There may be many paths to take, but they will converge on a number of solutions that are likely to be repeated wherever life evolves. Conway Morris's view is quite subtle. Even though, he says, the possibility of intelligent life is already laid down in the basic structure of the universe, the deep structure of the universe indicates life's inevitability. Nevertheless, life may be very rare or even unique to this planet. That is because conditions for its existence need to be just right. We would need planets of the right size and distance from their local stars, with large satellites, some protection against stray comets, and an atmosphere to ensure just the right amount of safe radiation from the nearest star, which also needs to be just at the right stage not to fry or freeze the planets in question. These conditions are so various and so precise, and need to be so exactly correlated.
I'm on my way to talk to Stephen Hawking about some of the questions we are both still asking. I want to ask him his views on evolution. As a physicist, does he think that the origin of life on Earth is just a happy coincidence?
The existence of the Earth and the properties that made it possible for biological life to develop depend on a very fine balance between the so-called constants of nature. If they were more than slightly different, either planets like the Earth would not occur, or the chemical processes necessary for life would not take place. One might take this as evidence for a divine creator, but an alternative explanation is what is known as the multiverse. The idea is that there are many possible universes. Only in the small number of universes that are suitable will intelligent beings develop and be able to ask the question, why is the universe so carefully designed?
The apparent fine-tuning of the universe is one of the hottest and indeed most controversial topics in our intellectual life today. Among physicists, argue about it among each other, philosophers, theologians, and then philosophers, theologians, and physicists all together. I want to get your sense, first of all, about the legitimacy of the question in terms of, is the universe fine-tuned, particularly the initial condition?
Well, the universe is certainly fine-tuned in the sense that the initial state of the universe was extraordinarily special. Now, there's fine-tuning in the origin of the universe, which has to do with the second law of thermodynamics. It has to have been extraordinarily precise, and in fact, it has to have been at least as precise as 1 part in 10 to the power 123. Now that's
it's an
a ridiculous
extraordinary number.
It's a ridiculous number, yes. That's right. And it's nothing like, people worry about the constants of nature. You see, you want to fix those constants. Okay, they're just a few numbers. 20 numbers maybe.
Yeah.
And those have got to be fixed to, I don't know, just a certain amount of precision. And that's nothing by comparison with this number. The precision that we see in the initial state of the universe completely dwarfs any of these other considerations.
And that level of precision is so impossible to conceive of as from some random point of view. I mean, that's not something that you can achieve in a random fashion under any. I mean, in infinity you can do anything, but obviously, but that's a.
It's no explanation. I mean, that's right. I mean, you can't say, well, there are lots of universes, and out of that particular one, which we happen to be in, that number was that thing. Well, no, it doesn't explain it. You don't get anywhere close to that number.
Right. What is the implication then in terms of the generation of such incredible precision? Can the argument of multiple universes achieve that?
Well, I don't think any of these are going to, you see, it's such an improbable. We're talking about how special the Big Bang was.
Yes.
Now, you could imagine other Big Bangs which weren't so special. But, I mean, you can have other Big Bangs not so special, but that's not what we've got.
Yeah.
See?
And we're here in this one.
We're here in this one. We could have been here equally well in zillions of the other ones, you see, which weren't so special. You could have a universe which is special in our neighborhood. Our galaxy could be just as it is, but the distant universe would be different and not special out there. And that's much more likely. If you're just talking about probabilities, all these other alternatives are far more likely than the one we see, which is saying we're here and that's why the universe is as special as we see it, doesn't go anywhere to explaining the specialness of the Big Bang. It's just, it gets you nowhere because we don't need the universe to be that special for us. It's not any use to us at all why the distant universe is incredibly special and why it came from a Big Bang, which is just part of the Big Bang, which is just as special as the part we came from. And you can't say, another argument, you can't say, well, okay, you could have got lots more people by having a bigger universe. That doesn't work either, because there's lots of cheaper ways of making lots more people. You make lots of universes. And it's far cheaper in the sense of improbabilities, that's to say it's far more probable, to make lots of universes with a few people in each one than to make one universe full of people. I mean, that's just a simple way of saying it.
In a sense, this is an even deeper mystery than the anthropic people normally put out for us.
Yes, it is, yes. No, it needs a scientific explanation. It needs a good physical theory to say why the Big Bang had that nature that it did. And we have no theory which really explains that. I mean, people usually say it's quantum gravity. No quantum gravity theory I've ever seen incorporates the asymmetry in time, which is necessary to explain why the Big Bang had this special nature, and not the singular states which come from black holes, collapses, and so on. There has to be something asymmetrical, because the second law of thermodynamics is asymmetrical. And any quantum gravity theory, which is going to explain why the Big Bang has this special structure, has got to have that in it. And no theory I've ever seen has that character.
You see, Einstein believed in another God, the God of Spinoza, the God of Leibniz, the God of order, harmony. The universe could have been random. It could have been chaotic. It could have been messy. But the universe is actually quite elegant, quite simple, and in fact is gorgeous. You can put the laws of physics as we know them on a simple sheet of paper. Amazing. Didn't have to be that way.
Why does mathematics work? Think about it. Mathematical entities like numbers, sets, and equations are non-physical and abstract. They can't cause anything. Yet, for some reason, the physical universe operates mathematically. As Galileo put it, the book of nature is written in the language of mathematics. Scientists do not use mathematics merely as a convenient way of organizing the data. They believe that mathematical relationships reflect real aspects of the physical world. Science relies on the assumption that we live in an ordered universe that is subject to precise mathematical laws. Thus, the laws of physics are all expressed as mathematical equations. For example, Pythagoras discovered that when a vibrating string is shortened by half, it plays the same note one octave higher. Isaac Newton's observations led to his discovery of the law of gravity, a mathematical relationship expressed as a simple equation that enabled us to enter the space age. Mathematics enabled astronomers to pinpoint the location of a previously undiscovered planet. And James Clerk Maxwell used mathematics to predict the existence of radio waves. Albert Einstein, working with theoretical mathematics developed 50 years earlier, formulated his general theory of relativity, a pillar of modern physics. His calculations were later confirmed during a solar eclipse, when Arthur Eddington observed light from distant stars bending around the sun. Then, Peter Higgs used mathematical equations to predict the existence of an elementary particle. It took 48 years, billions of dollars, and millions of man-hours for experimental scientists to finally detect the Higgs boson. How do we explain the astonishing applicability of math to the physical world? In 1960, the Nobel Prize-winning physicist and mathematician Eugene Wigner published an article that stunned the scientific community entitled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." Wigner concluded that the effectiveness of mathematics is a miracle, which we neither understand nor deserve. Why is mathematics so effective? Philosophers who address this question fall into two camps. Naturalists, who believe that all that exists concretely is space-time and its physical contents. They exclude supernatural causes. And theists, who believe in a God who created the universe. Naturalists cannot provide a reasonable explanation for why mathematics applies to the physical world. It's just a happy coincidence. But this is no explanation at all. At most, naturalists can say that it's not surprising that math applies to the world, because the world itself just happens to have a mathematical structure, so of course mathematics applies to it. But this explanation is unsatisfactory for two reasons. First, a great deal of mathematics in science cannot be physically realized. For example, imaginary numbers and infinite dimensional spaces. Although these concepts are useful, physical reality cannot possibly have the structure they describe. And second, this answer still doesn't explain why the physical universe has such a stunningly elegant mathematical structure.
By contrast, for theists, mathematics works so well in the physical world because God has chosen to create the world according to the plan he had in mind. The first-century Jewish philosopher Philo of Alexandria offered this analogy. When a king wants to build a city, a trained architect first designs in his mind a plan of all the parts of the city that are to be completed. Then he begins to construct the city out of stones and timber, looking at the model and ensuring that the material objects are built according to the plan. Mathematics and physics work so well together because the same mind that designed the universe on a mathematical model also built the universe on the same mathematical model. All of this adds up to an argument for the existence of God that goes like this. If God does not exist, the applicability of mathematics is just a happy coincidence. But the applicability of mathematics is not just a happy coincidence. Therefore, God exists. Eugene Wigner was right. The effectiveness of mathematics in the physical world is quite literally a miracle, which is best explained by the existence of God.